So the proof actually is, well, somewhat different. So what you do is you have this, right? Now we can sum this over gamma prime. Here we have a free parameter gamma prime. So you sum this over gamma prime for gamma prime less than n. And of course you get that this is the same as I had here, so I forget about this, right? There's no n here. Just take this definition. And I sum over gamma prime, so the only thing, the bound that I have now is that it's actually not an upper bound, it's equal by definition, right? Sorry, I had the expectation, no, it's sigma omega, so it's equal to this, right? Because I just sum, and that's the number of terms I have in my sum, right? They are all bounded by the same, they are all equal to that. Well, actually, I should put this, yeah, sorry. That's not good, because this depends on gamma prime. Right? And what I know is that this is finite, right? So I put this here, so it's the sum over gamma prime less than n, right? And this I call sigma omega n, and we know that E sigma omega n is bounded, oops. This thing is actually, let's just take its average. So this is 2 omega tilde n, and E sigma omega n tilde is again bounded by the constant C I had up there, right? So, sorry, this I call the blah, 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 where, oh no, I had this one, yeah. And this is bounded by a constant which doesn't depend on n, because I put the n, I factor the n out here. Right? They're all bounded by the same thing. And so if I take this here, right, of course now in here I can restrict, I decrease this sum if I only consider the eigenvalues that have a center of localization less than n. Right? So this inequality is still an inequality. Right? Because I restrict to those. But if I restrict to those, I can actually take gamma prime for each of eigenvalue in here to be gamma c. Right? Meaning that I will get that this sum with gamma c, right? I can intervert, I can put this one in here, and I just take, forget about the sum here, I just take gamma prime equals gamma c. I get this. But now, because phi gamma c is a maximum of phi gamma, this product is going to be larger than phi gamma squared. What do I get? I get that if I take the sum over the energies that have a localization center of modulus less than n, the sum over gamma phi gamma squared times this is less than my sigma tilde omega n. Right? So it means that for all energies that such that gamma c is less than n, I have this is less than sigma tilde omega n 2n plus 1 to the d, right? And then I just take the square root, just forget about the sum here, take the square root, and I get what I announced with exactly d over 2. I can certainly, well, I need to be a bit sharper. I need to do it between n and n plus 1 to be able to replace 2n plus 1 by gamma to the power d, right? I wanted to have gamma c to the d here. So I need to do it in a layer so that gamma c and n are about the same size, okay? But I get exactly this estimate, okay? Except that I get rho over 2 here instead of rho, right? But I get a similar estimate, this kind. And so this is what you get mathematically. What is it? Physicists have worked on these questions for a long time, and when they describe a localized eigenfunction, what do physicists say? Well, physicists, they write the following thing. For all eigenvalues, phi of gamma is bounded by a constant. They don't care whether it depends on omega or not, minus some universal constant, so roughly in the mind of the Lepunov exponent, gamma minus gamma c. And there is no prefactor depending on gamma c. So the question is, where is the truth? Right? Is there a prefactor or not? Okay? And so that's the question I'm going to answer. Okay? And
but also here you have rho 2 and here you have rho, right?
exactly. So the value of rho, the problem is that, well, I should call it rho tilde. They never tell you what rho tilde is, right? It could be rho over 2, it could be rho, but it's what is the precise decay rate, right? For this to be correct is a good question. Okay? But, oh yeah, another question. It was known since works of Simons in the 80s, in the 90s actually, not in the 80s, in the 90s, that this cannot hold. Mathematically, right? It's not possible that such an operator has so strong restrictions, meaning that the rho doesn't depend on n, right? So the problem is it depends on the volume. That C doesn't depend on n, rho doesn't depend on n. So this is called what is called uniform localization. This result is called was called semi-uniform localization estimate, right? This is called uniform. And it was known since works of Simon in the 90s that this is not possible. With any rho tilde, right, except 0. Right? It's not possible that you're going to have this with any rho tilde except 0, which is not the most interesting one. Okay, with any positive rho tilde. And so the question remained, what is the truth, actually? And therefore, I'm going to define something which is actually not related to localization, but which is just, well, can define it for any function, at least in a finite cube, right? But also in the infinite volume. So imagine now that we know our assumptions. So for the theorem to hold, I need some assumptions, but before that, I need to make a definition. So imagine now that you have a function that satisfies exactly this kind of estimate. Assume that there exists mu, right, positive, and you have a function phi, so phi in L2 of ZD, right, such that the sum over gamma in ZD, actually it can be, well, it's not good, it's not important that it's ZD, right, but I'll do it on ZD, right? You can do it in subsets of ZD and so on, that's fine. Satisfies sum of e to the 2 mu x phi of x is finite. Right? That for some mu, you know that this has exponential, sorry, squared here, this has exponential decay at infinity. Assume that you know that this has exponential decay at infinity. Then you can always define the following thing. Well, actually, I want something more. So I had gammas, so this is gamma minus gamma prime, gamma, right? And for any gamma prime, you know that this is finite. Okay, take it. And then you can define set. So for mu less than mu, or actually even for mu, set m. So let me just write the notations to be the same. M of L mu what do I have? Gamma prime and phi. Gamma prime, or rather phi and gamma prime, to be the sum over gamma in ZD of e to the 2 mu gamma minus gamma prime minus L plus gamma squared. Right? This is this is well defined. Where, of course, for a real number x, x plus is the max of x and 0, right? For x real. This is a nice finite number, right?
Does it mean max of x and 0?
X is a real number, so you know what max and x and 0 is.
Okay, positive part, yeah, positive part, yeah.
Exactly, it's the positive part of x, right, of a real number. So it's the number if it's positive and 0 elsewhere. Okay? So of course this is finite because it's simply bounded. So I take always phi L2 and I always take phi 2 equal 1, right? As this is actually less than 1, right? Because this is positive. So it's certainly less than this. What do I say? No. It's larger than this sum. It is finite by 1. And it is always larger than 1, which is the norm of phi squared. Sorry? Oh, gamma, yeah, sure, of course, yeah. Thanks. It is gamma, right? You always have this. And of course, you also have that m L mu of phi and gamma prime. This goes exactly to what? To 1.
And what is L?
L is just a real number, right? It's a parameter. It's positive. It's a real positive number, yeah. And you have that this, it converges to 1 as L goes to plus infinity, right? Just by dominated convergence, right? So you make ask, let L that depends on phi and mu, right? And gamma prime be the smallest, the min, the smallest L, such that m L mu phi gamma prime is less than twice. Where is it? So than 2. So which is this is 2 times m L. M mu plus infinity of phi and gamma prime. Right? I just want to know what is the smallest L such that you have that this is less than 2. I can take 2 can be replaced by any number larger than 1. Okay, I can define this. And this thing I will call this L here, I will call the onset of the onset length. What does it mean? Obviously, two is not important. Can be anything larger than 1 strictly, right? 2 is not important. Actually, you see there is a catch about this. Okay, there is a catch about this, but 2 is not important in the proof. And so this is the onset length. Okay, onset length or onset the length of onset of localization, right? So we call it. So it's the length.
Localization length.
No, it's not the same. Localization length is already taken, right? Localization length in physics is the asymptotic behavior at infinity, right? This has not to do with the asymptotic behavior at infinity. It's the number mu that has to do with the asymptotic behavior at infinity. So this is length of the onset of localization. So what does it mean, the onset? It means when the localization does start, right? When does localization start? So, and what is the point gamma prime that we, so if you're dealing with functions that satisfy this for a given gamma prime, right? You can define this. And of course, if you deal with localized function, as in the previous example in this random case, you can take gamma prime to be a center of localization, right? So for phi an eigenvalue of h omega lambda, you can take L of phi and mu, right, to be L of phi, mu, and gamma c, one of the localization centers. And actually, you can even take the minimum over the localization centers of phi. Right? Phi is an L2 function, so it decays at infinity. So there are at most finitely many points where it reaches its maximum. Right? So it's going to be taken the minimum as this in the localization case. But this is all completely general, right? This is a completely general nonsense. And you can define this. And of course, by the definition and the soup in there, one has that phi of gamma is less than e to the minus mu x minus x gamma minus L phi, I'm sorry, not x gamma, minus gamma c. So this is gamma, gamma minus gamma c, phi of gamma, and this depends on mu, plus. And here we have, well, what do we have? We have 2. Well, square root of 2, actually.
So, Frédéric, excuse me, can I just check that I understand what you are doing? You are trying to capture the localization center by some averaging characteristics.
No, what I'm trying to capture is not the localization center. What I want to understand is, I have a localization center. How far away of the localization center must I go to see actually the exponential behavior starting? Because you see this here, well, when do you see this really decay exponentially? It's when you're outside the circle or the disk of center gamma c, radius L. In there, you don't see anything, right? Just see bounded by 1. This is a function which is L2 norm, right? It is bounded by 1. That's fine. But outside, you see this. So if you want, around every center of localization, I have a disk, right? And in this disk, the best bound I can give is 1, right? I can't give anything better than 1, which is what I have. I have a square root of 2 here, but you can replace this by 1, right? And there, outside here, you see exponential decay. So this is why we call this the onset of localization, because this is really where you see things localizing, right? You see the exponential decay. Okay. So, in particular, what you can show is that if you have 2 localization centers, right? The distance between, so proposition, if gamma c prime or gamma prime c localization centers of phi, then you have that the distance between the 2 points is bounded from above by, well, L mu of gamma c, for example. I'm sorry, where did I put the gamma c? Oh, L. So I have, well, L, I can put here, L mu phi, right? And plus dimension over 2 mu, and here I have the log of 2L mu phi plus 2 kappa plus 1, where kappa is a real number such that e to the, right, kappa is defined by this, just constant over mu, right? Kappa is constant over mu for a fixed constant that can be computed from this equation, right? And what you see is that when the localization onset length is growing larger, well, localization centers cannot be far away from one another, not further than essentially the onset length, right? All the localization centers roughly lie inside this disk. Okay? So that's one of the things that you see. And the second thing that you see is that well, one has, if L phi mu is equal to L phi mu gamma C, right? So you take the localization center where you have exactly this distance, this onset length, right? That's the smallest one. Then you have the following. You have that phi of gamma is bounded from above by the sup norm of phi, which is less than 1, but it may be much smaller than 1, times e to the minus mu x minus, gamma minus gamma c minus not the onset length, but something which is slightly larger, L tilde of mu and phi, where this is actually, oops, L tilde of mu and phi. Plus, of course. If you remove plus, you of course have the same bound. But, and so you see that, right? Here, inside this disk, it's of course never less than that. But even outside, if this one, inside the disk, for example, imagine that the disk, the function is flat in here, right? And has small infinity norm, then the exponential decay outside starts from this small infinity norm, right? It's not, you see here the square root of 2, which didn't depend on phi infinity, but actually you can replace this by phi infinity. Okay? And the main result of our study is the following.
So you replace simple exponential by slightly more interesting ansatz, right?
Exactly. Exactly. What you leave some room for the function being, well, not exactly flat, but not decaying uniformly inside some. Here it's a disk, but it doesn't really matter, right? I mean, you could take squares, whatever you want. But the important thing is the following. Theorem. So take, let H omega, let be the Anderson Hamiltonian. The one I wrote above, right? For lambda large enough so that we are localized in any dimension. Exactly, it's the one that I had on the board, right? It's actually the proof in the paper, the proof is valid for any model for which you know localization in the sense that you have a bound on the correlators, right? Any model like this. Actually, even something weaker. But I will just speak about the Anderson model. Then I can do the following thing. Then you can count with probability for any p larger than 1, for example, with probability larger than 1 minus L to the minus p, right? If you count the number of eigenvalues, E, eigenvalues of H omega lambda, such that such that what? Such that the localization, the onset length, not the onset length, L mu of phi, right? So phi is the associated eigenvector, of course, is larger than L, right? So count the number. So what you're doing is and gamma c, you have a localization center, right? Which is within the cube. So here you're in infinite volume, right? You have infinitely many, countably many eigenfunctions, right? And you just keep the number of those that have localization center less than L, right? Then, if you count all of them, right, without this restriction, if you just take this, then the number of those should be 2L plus 1 to the power d, roughly, right? Because you see, the picture is the following. You take all your eigenfunctions, right, that are localized. And now I cut, and I take those that are inside here, okay? Because they are localized, Essentially, if they live here, not very far away, the localization center, so there may be a little bit, some part of it outside, but the number of them, right, you're sure is of order 2L plus D1, right? Then this number, so this quotient.
The order of the size of the box, yeah?
Exactly, size of the box. This number is bounded by e to the minus, what was it? Some constant c that depends on nu times L. So what is nu? This is for any nu less than mu, and that's the exponent in star, where star is just this initial estimate. Right? So you know you have some localization property with a rate mu. Okay? Then, to have a large localization, a large onset length, is very unlikely with a good probability, or meaning that you have very few of them.
So it means that they don't overlap too much with any.
Well, they can overlap, right? They can overlap because this depends on the distribution of the localization centers. Right? You see, you have these disks, so you have these bores. So, but there are not many bores with a large radius. Right? So in a way, this speaks for the physicist's intuition that most of the eigenfunctions actually start to localize very quickly. Right? That the number of them that localizes only after leaving a big ball, right, is actually very small. Okay? And what you can show for the same model, there is a lower bound. The lower bound is actually not that easy to obtain, but what time is it, by the way? Okay, 10 minutes. Okay. So, yeah, okay. Well, so the lower bound theorem. So what you can do, theorem. So of course now, yeah, one thing you can do is you can look at. So from this theorem here, you can actually show, this is using self-averaging, I use the IID part self-averaging. You can show that if you take this number, and here you put this, divided by 2L plus 1 to the D, then this almost surely converges to some limit, right? Which is not the density of states, it's the density of states with restrictions on the localization centers, right? So this is n of, so you can take, sorry, you don't take all of them, you take only the ones, yeah, not exactly this because otherwise there's only one number left, but what I want is I'm going to take the eigenvalues less than E such that L mu phi is larger than L and gamma phi or gamma C I called is less than L, right? Divide this by 2n plus 1 to the D, and this converges to some, well, to the distribution function of some measure in two variables, right? What did I call this? And yeah, this depends on u, right? Because I have, this is not mu, this is nu, this is nu. This depends on nu, right? So what I do, I take this counting function, and I restrict also the energy.
What is nu?
Nu is any number which is less than the mu here. If I have this one for a number mu, I also have it for something which is smaller, right? And I need to get something, I need to take something smaller to be actually able to make something out of this.
Some number smaller than the Lyapunov exponent.
Well, no, that's a good question, but it's not, this is actually not, even in the 1D case, it's not the Lyapunov exponent. Yeah, I'm going to explain this. It's not the Lyapunov exponent. It's something which is smaller. Actually, the best results in 1D you get that the mu here is half the Lyapunov exponent. It's much strictly smaller. And it needs to be. Well, I'll explain where it comes from. So, okay, you get that this converges to some, and this is a distribution function of some probability measure on, this is the spectrum of the random operator, and this is just R plus, okay? And then what you can show, you can study, so what this tells you immediately is that this n nu of E is, so a corollary of the theorem up there, the theorem implies that this is less than what do you have? E to the minus C nu L, right? You have something like this. Right? This is just because this number is certainly bounded by that limit, okay? And so you have this. But now what you can prove is that, you can prove the following, is that a lower bound, nu of E and L, is larger than the true density of states at the energy E plus some constant, so there exists a constant positive, such that for nu less than mu and L small enough, L to the d minus 1. So this is the true density of states, right? That's the IDS of H omega lambda. Okay? And so in particular, if you look at what's happening at the bottom of, sorry, this is, it's not, of the whole spectrum. Here I take the whole spectrum, so it's, the whole spectrum is finite, of course, but this is E minus, where E minus is the infimum of the spectrum of minus Laplacian plus V omega. This is an almost sure number, right? That's the infimum of the spectrum is almost surely the same for omega. You have this. So what this shows, so this thing is well known. Sorry, there is a minus missing here. It is minus d minus 1. This goes to 0. This thing goes to 0 when L gets large. Right? And Lifshitz-Tay's estimate by Lifshitz-Tay's, we know that n of E minus plus C L to the minus d minus 1 is larger than, well, E to the minus a constant, call it kappa, L to the minus, what do I have? D plus 1, D over 2. Right? So in dimension 1, sorry, there was a minus here, and so that's correct. If d equals 1. So in dimension 1, you find that the upper bound that I got here, except the constant is not the same, is the same as the lower bound as far as L goes. But this is not optimal.
So Frédéric, so how do you normalize your true density of states? This is the number of eigenvalues below this, below what?
Yeah, exactly. Below. So this is why I count this goes to 0 when you let L go to infinity, little l go to infinity.
Okay. So the left-hand side is obviously less than or equal to the density of states if you put the same parameter.
Yes, exactly.
But, so you prove it.
Exactly. This is actually here because I take plus infinity, right? I mean that I just look at what's happening. So for the true density of states of this one, it would be 1, right? Because I count all the eigenvalues.
Yeah.
Okay, really, I don't put any restriction on energy here, right? I just count all of the eigenfunctions, right, that have localization, onset length larger than L. And I show that if you count them all, you get something larger than this. I don't look only at those that have larger energy. You can actually restrict the energy, right? I mean, you don't need to take them all, but you could restrict the energy.
So when L, just a second, when L goes larger, the right-hand side goes to 0.
This goes to 0, exactly, just like here. When L grows large, this goes to 0, exponentially. Right? I want to see whether this bound has a chance of being sharp, right? In 1D it is. But you see, okay, now a remark. Within here, when you are inside the onset disk, many different things can happen, right? So we have this onset disk, and outside here you have nice localization, right? But when you're inside here, the function can look very different, right? Because it could be, for example, that your function is here very flat, oscillating. But it could also be that inside the onset disk you have something like this, then a number of bumps, right? And then you're oscillating, right? It need not be flat. So you can have actually almost localization centers inside there in arbitrary complexity. The picture in there can be very complex and it's quite different. And so to phrase...
What is the most probable?
Well, that's a good question. I don't know. It's all of them happen, that's for sure. They all happen.
What is the typical value of L, small l?
There is no typical value of small l. There's no, it's a probability distribution, so where do you put the threshold? I mean, what do you call typical? Where from do you start not calling things typical? Right? There's no typical value. They all happen. Well, I don't know what the mean value is. I don't know, but I'm not sure it makes any sense. We know that the distribution is integrable, right? Because we just have a tail estimate, but I don't know what the mean value is. Right? Moreover, they depend on you. And that's very important because you see, the way I cut things off, the way I define things, if I still have it on the board over there, no, I don't have it anymore, but, oh yeah, here it is. The way it depends on mu. Actually, the mu here, where I wrote it should be outside, it should be this. Right? The mu is outside, right? It's not, I don't want to have L depending on mu in such a gross way. I'll keep it this way. Okay, the mu is inside, it's outside the parenthesis here. It depends on you. And in particular, right, I want to come to actually the question that you asked is that, you see, we did some numerics, so I won't take time to present them because it's going to be too long, but we did some numerics. And one thing that you notice is that the mu that you need to take is actually very important. And it's easy to understand. So the fact that, you see, for such a sum, so the first thing you want to start with is you don't start with an eigenvalue. The first thing you start with is a sum of the following type. You sum over the whole spectrum, right? You do this sum over the whole spectrum. We know that this is finite, right? That's our initial estimate, the one I gave you before.
The sum of all the eigenvalues.
Exactly, over all the eigenvalues of this. And this is, it's going to be finite, well, it's going to depend on omega. But what happens is that if you take, numerically, if you take a finite sample, if you want to see this, right? What's going to happen is that this is going to be an extremely large number, right? Because there will always be, it's not going, for example, it's not going to be the Lyapunov exponent that drives this. Why? It's because when you take such a sum, what is going to be the most important part is this one. It's not so much the size exactly of that one, right? It's this super exponent because there will always be functions, right, which are not inside the Lyapunov behavior when you take this sum, meaning that they will be exceptionally large. And there will be not many, but very few are enough because of this, the exponentially growing factor in here, as long as you take large length. Right? And it is this factor that's going to dominate. So when you say, you see, probabilistically, you know that almost surely the functions all reach Lyapunov behavior, right? But the problem is that even a small probability will have a dramatic effect on such a sum, right, because of the super large factors that you have in here.